Welcome to a video on verifying trigonometric identities. These are the identities that we've already seen in this course in earlier chapters. So the first ones, the reciprocal identities, these are how the six functions are related to other functions as being a reciprocal of those functions. So the sine and the cosecant, and the sine, the cosine and the secant, tangent and cotangent. Right. So there is a function and a cofunction that are reciprocals of one another, but tangent and cotangent are the only cofunction pairs that are reciprocals of one another. The others are sine and then cosecant, and then cosine and then regular secant. So those are the identities again that we've already seen. Hopefully you already know those. The quotient identities, that's just the fact that tangent and cotangent can be written as a ratio of sine to cosine or cosine to sine respectively. And then there's the Pythagorean identities. This is from the fact that the unit circle has a radius of 1 and sine and cosine are the x and y coordinates. So we get right triangles inside the unit circle, and all those right triangles created have a leg, and a hypotenuse of 1. So that would be cosine squared sine squared equals 1 squared. So that's where that's coming from. That's just the Pythagorean theorem. And then the other two are coming from taking the original sine squared cosine squared and dividing through by first cosine to give us this one. If we divide through by cosine squared, we'll get a tangent squared. And then if we divide this through by cosine squared, we get a 1. Alright, and if we divide this by cosine squared, we get secant squared. Alright, and then the same thing would happen if we divide it through by sine instead of cosine. We'd get a 1 here, sine divided by sine. Cosine divided by sine is cotangent, and then 1 divided by sine is cosecant. So that's where these things are coming from. This is just Pythagorean theorem, Pythagorean, and then these are just taking that original equation and dividing through by either sine or cosine. You can see the other two. Alright, the even and odd properties. This has to do with the fact that on the unit circle, if you think of x as the angle we're rotating, if we go up rather than, down rather than up, that would be negative theta. The x-coordinates would be identical. The x-coordinate that we go up or down from would be the same if we rotate it up or down. And remember, the x-coordinate is given by the cosine. So the cosine of the negative angle is the same thing as the cosine of the positive angle because we have the same x-coordinate. But the sine of the negative angle, since we're going down rather than up, we end up positive here, negative here, but we would end up at the same absolute value, the same distance traveled up vertically, which is, remember, the sine is the y-coordinate. But we get the opposite. Right, and then because of the negative and then the positive, remember, tangent is sine over cosine. So tangent of negative x would be sine of negative x over cosine of negative x. So sine of negative x is negative sine. So we stick that negative out in the front. Cosine of negative x is positive cosine. So we end up with negative divided by positive. So that's sine over cosine's tangent, and we end up with negative tangent x. Okay, or you could also think of it as, remember, tangent being slope. So if I rotate upward, I've got a positive slope. If I rotate downward, I've got a negative slope. But obviously the absolute values of those slopes would be the same because we started off horizontally and we went the same angle up and the same angle down. So the slopes would be in absolute value the same, but they would be opposite signs. All right, and then obviously because of the reciprocal nature of the other three, if we stuck these negative x's into the reciprocals of these sines and cosines, we get the same property. Meaning here we get a negative, here we get a negative, but with secant we get a positive. All right, verifying identities. That's the big idea that we're doing in this section. really big thing you got to understand is to verify an identity, we can only manipulate one side of the equation at the time. Meaning, like down here, if I wanted to do this, I couldn't divide both sides by the secant. Right? Why is that? Well, if you divide both sides of an equation by some expression or some number, you are making an assumption that this equal sign is true. Dividing both sides of an equation, like if I had, 3x equals 6, and I divided both sides by 3, that is under the assumption that this equal sign was true to begin with, that 3x really was equal to 6. So the properties of equality that you use in algebra to solve equations are all based on an assumption of equality to begin with. That if you go back and look at some of those, the addition property of equality, the multiplication property of equality, it says if A equals B, then something like A plus C equals B plus C, or you could do A over C equals B over C. That's the addition and multiplication, which technically encompasses division, properties of equality. But it starts off with this: if they are true to begin with, then I can do this stuff. So if we're doing this stuff, if we're adding something to both sides or dividing something from both sides, then we are operating under an assumption of equality. Well, that's not what we're being asked to do here. We're being asked to verify that it is true. We're being asked to say, show that this side is equal to this side. And if we do something to both sides, then we're just assuming that the equality which we're being asked to prove is already true. So that's why we can only work with one side or the other, but never both. Okay. All right, and then it says start with the side containing the more complicated expression. So over here, just because there's two things rather than one, I would use this. Now, secant, cotangent, cosecant, a very common thing to do. It says up here to use the fundamental identities. So a very common thing to do is switch everything to sine and cosine if you don't have any other guess of what to do. So secant is 1 over cosine. Alright, cotangent, if you remember, cotangent was cosine over sine. And then cosecant is 1 over sine. Alright, and then just note, all I did is I worked independently. I changed this to its reciprocal, changed this to its definition, or its reciprocal definition, changed this to its ratio definition, change this to its reciprocal definition, and then just simplify. Now again, I'm just working on the left side. I'm not dividing both sides by anything. I'm just cleaning this up. There's a cosine above and below, so I end up with 1 over sine equals 1 over sine. Now I could have left this as cosecant, which would have been fine, to just not work with it at all and just show that I get the other side. So cosecant x, and then 1 over sine is cosecant x. And then I have proven the identity. I've shown that by manipulating only one side that I get the other. Now it would have been fine if I would have changed this to 1 over sine and then just at this step show that they are equal. That would also verify the identity. By manipulating the left and manipulating the right to get 1 over sine, I've shown that we get equality, that the two things are equal. So either way would have worked to verify the identity. Alright, let's try another one. Okay, I got a sine tangent plus cosine equals secant. This one's the more complicated side. It's got more to work with. So I'm going to call this sine times, instead of tangent, I'm going to write it as sine times sine over cosine plus cosine equals secant. Alright, now same thing as before. I'm going to get a common denominator here. So if I get a common denominator, it'll be cosine. This is sine times sine is sine squared over cosine x. Alright, common denominator, I would have to multiply. Remember, this is like cosine over 1. So to get a cosine for the denominator, I had to multiply the 1 by cosine, so I have to multiply the top by that, so that'll give me a cosine squared. Alright, and then if I add these together with the common denominator, I'd have sine squared plus cosine squared over cosine equals secant, and hopefully you can see what I'm going to do next. This is the Pythagorean identity. Sine squared x plus cosine squared x is 1. Alright, and then 1 over cosine is defined to be secant. That's a reciprocal identity. So secant equals secant. I've shown the left side to be equal to the right side. Alright, so get a common denominator after you've changed everything to sine and cosine. Very common idea is to get the common denominator when you have one piece that's written in fractional form and another it's not. You can always write it in fractional form and get a common denominator and see what happens from there. It's also very common to start these things and realize that an idea is not working and then have to go back and fix things. Alright, everything's already in terms of sines and cosines here. What we typically do in this case when we see a common factor is to pull out the greatest common factor. So on the left side here, if I pulled out a sine, I would be left with a 1 minus and then a cosine squared. Alright, and then this right here, notice if sine squared x plus cosine squared x is 1, if I subtract cosine squared from both sides of this identity, I end up with sine squared x equals 1 minus cosine squared. Now, I'm just showing you where this is coming from. You don't have to show this in the middle of your work. It's just that Pythagorean identity and all forms of it, meaning if I go back to my Pythagorean identity, I could move the cosine squared over as we did. I could move the sine squared over as we did. I could take the square root of both sides if I needed to. I mean, all different forms of this are included with the base form, the sine squared plus cosine squared equals 1. So when I see something like 1 minus cosine squared, I can replace that with sine squared because they are equivalent. And that's all I'm going to need on this one to prove what we're trying to prove. Alright, sine to the first times sine squared is sine to the third, so sine cubed. And that's what we were out to prove. Alright, so you can manipulate known identities to make them look like things that pop up in your problem. But again, you could not divide, like right here at this step. I can't divide both sides by sine and get sine squared equals sine squared. Okay, I have to go through and only work with one side. Notice I never did anything to the right side. I just manipulated the left and made it look like the right. Alright, a very common thing here in problems like these would be, again, change it to sines and cosines. And if that doesn't give it to you, a lot of times what we end up doing is multiplying the top and bottom by fractions by the same thing. Alright, now cosecant, remember cosecant is 1 over the sine. Cotangent is cosine over sine. Alright, and you see just by rewriting things in terms of sines and cosines, I get this expression. I just have to combine the numerators over the common denominator. So a lot of times all we have to do is, to get the ball rolling in the right direction, is switch everything to sine and cosine, and we can, a lot of times we'll just be able to see, alright, this is what I need to do from there. Alright, this is a very common thing, multiplying numerator and denominator by the same factor in order to verify an identity. So, and again, notice everywhere on the left side we've got sines and cosines. Everywhere on the right we have sines and cosines. So what we've been doing, switching everything to sines and cosines, that's already done here. We don't have it. We don't have that luxury to do it this time. So let me show you what a very common thing to do in this case is. I'm going to multiply the top and bottom by the reciprocal of this denominator. Alright, now you may be thinking, well, why would I do that? Well, the reciprocal of 1 plus cosine is 1 minus cosine. And you remember that would look like a difference of squares. 1 plus cosine, 1 minus cosine. And what excuse me, what happens when you multiply a difference of squares? You get these two factors in the difference of squares, you get a difference of squares. I mean, you get 1 times 1 is 1, and then you'll get a minus these two multiply together, which is cosine squared x. Alright, and as we just saw a little bit ago, sine squared is 1 minus cosine squared x. So I'll be able to bring a sine squared in on that denominator. Alright, so a very common thing to do when I see these, when I see a 1 plus cosine and a 1 minus cosine, the thing that starts popping in my head is, or not just cosine, 1 plus sine, 1 minus cosecant. Any of these things that have the Pythagorean identity look to them. If I have anything that has a 1 minus a secant or 1 plus a secant, I would think that. It's just that nature of the Pythagorean look. Alright, so when you see those things, that should be something that pops in your head. When you see 1 plus or minus a trig function to the first power, then you should get in your head, alright, this may be a time to use the difference of squares. So I'm going to take the sine x over 1 plus cosine x, right? And on the top we'll just write it as sine x times 1 minus cosine x. Nothing we can technically do there. But on the bottom, like we said, we're going to write that as 1 minus cosine squared x. Okay, it's like FOIL. First one outside negative cosine, inside positive cosine, so they cancel, and then a negative cosine squared. And we just said that's the same thing as sine squared. So hopefully you can see what's going to happen. We're going to end up with a sine squared on the bottom, and then this sine and one of these sines on the bottom will cancel. And what are we left with? We're left with 1 minus cosine x over sine, which was the original right hand side. So we've proven the identity. Alright, and it's very common to just grab one side and work. Like I do, you will see me do, rewrite the left side and the right side together, but it's fine also to just take one side, work with just that one side and show you get the other side. Alright, here's another one. When just looking at it, I see this negative x. Anytime you see a negative x, more than likely we're going to use this stuff right here. So the cosecant of negative x is negative cosecant. So I would start off by changing that to a negative cosecant. So secant x minus cosecant x over secant times cosecant. And it says that's equal to sine minus cosine. Alright. And so again, I don't have to write that. I could just work with the left side if I wanted to. Alright, now secant x times cosecant x. Secant x minus cosecant x on the top. Again, it doesn't really matter how you proceed through this, but I would strongly encourage you at the start to just rewrite these in terms of their sine and cosine definitions. So cosecant is 1 over the sine, secant is 1 over the cosine, and then down here I've got a 1 over cosine times 1 over sine. Alright, now what I'm going to do here, a very common thing to do as well, is when you have switched from the other trig functions to sines and cosines, if that creates fractions within fractions, that's called a complex fraction. And a very common thing to do with complex fractions is to multiply top and bottom by the overall common denominator of those things. Well, the overall common denominator here is sine cosine. Alright, again, if I was like combining these, the common denominator would be sine times cosine. That's what we mean. That's what we're going to multiply by. And in doing that, I'm going to get sine times cosine divided by cosine. So that'll cancel a cosine and leave me with just a sine, minus 1 over sine times cosine. The sine this time will cancel and leave me with a cosine. Alright, and then on the bottom, sine will cancel with sine, cosine will cancel with cosine, everything's a multiplication. So we end up with a 1. Alright, and that is the right hand side, sine x minus cosine x. Anything divided by 1 is itself. So we've proven the identity. We get the right hand side. Alright, that's what we're after. We'll just manipulate one side and get the other side. Alright, same thing as before. When I see this, when I see 1 plus 1 minus, I'm thinking the difference of squares, 1 minus sine squared. Now where would that come in here? It's just going to be getting a common denominator on the left hand side. So the common denominator is going to be the product of these two. One's a plus and one's a minus. So the common denominator is going to be 1 plus sine theta times 1 minus sine theta. Alright, and then plus, same thing, common denominator is going to be 1 plus sine and 1 minus sine. Alright, and again I had a 1 on the top. Now, what was there before? There before was a 1 over a 1 plus sine. So 1 and a 1 plus sine. So what's new? This piece right here is new. So I need to multiply the top by 1 minus sine theta. Alright, and then likewise with the other fraction, this is what was there, 1 over 1 minus sine. So this is new, the 1 plus sine, so I need to multiply the top by 1 plus sine to keep the fraction true, right? It's just getting a common denominator. So these would cancel, leave me with what I had before. These would cancel, leave me with what I had before. So they're equivalent expressions getting these common denominators. Alright, now on the bottom, that's going to be a 1 minus sine squared. And on the top, I've got a 1 minus sine theta plus the bottom here, I've got a 1 minus sine squared theta and then a 1 plus sine theta. So because I have a common denominator, I can combine the two numerators. When I do combine the two numerators, I'll have a 1 minus sine squared theta on the bottom. I'll have a 1 plus 1 is 2. And then I'll have a negative sine theta plus a positive sine theta, which is 0. So I'm going to move that to there. Alright, now what is sine squared equal to? Or 1 minus sine squared equal to? That's equal to the cosine squared theta. Alright, now when I have cosine on the bottom, I could use this identity. Cosine's on the bottom, so that's secant. So 1 over cosine squared would be the same thing as secant squared. So that's what I'm using at this last step, is I'm going to call this, instead of 2 over cosine theta, I'm going to call that 2 secant squared theta. Alright, now look what I'm trying to get to. I'm trying to get to 2 times 1 plus tangent squared. So this was the left side. And now this is another very common thing to do, is to switch. I've been working with the left, okay, I can't get this thing to show up. Well, now I'm going to switch over to the right side. And if I can get the right to look like this, then I've verified the identity. So I've got 2 plus 2 tangent squared theta. The first thing I see there is a common factor. So I'm going to pull that 2 out. And then I have 1 plus 1 tangent squared, or just tangent squared theta. Alright, now 1 plus tangent squared theta, that hopefully looks familiar to you. If it doesn't, you need to train your eye to see it. But 1 plus tangent squared is another Pythagorean identity. 1 plus tangent squared is the secant squared, and if you notice, that's going to solve this for us. 1 plus tangent squared is secant squared, so there's 2 secant squared theta. right? And we've shown that these two things are now equal. So the right side, I can get it to look like 2 secant squared. The left side, I got it earlier to look like 2 secant squared. So that's another common thing to have to do, is to get as far as you can with one side, clean it up as much as possible, and then I don't know where to go from there. Well, this would have been where we went with it. If we would have shown that, all right, I can rewrite secant squared as 1 plus tangent squared, distribute the 2 through, then I would have been able to complete it. But if you can't see that, then that's a common thing to do, is just stop working with one side and start working with the other and try to make them meet in the middle. Alright, finally here's some guidelines for what we would want to do with these problems. So you can pause this and make some notes on this. But a lot of them are the things that we've done in here. Alright, this is the most common thing to do. Rewrite everything in terms of sine and cosine. But then some of the other strategies that we did here is factor out the greatest common factor, like we did on this last problem and a previous problem. Get the quotient written in 2 terms or combine them into 1 term. It's a two-way street. Sometimes we go this way with it, split them up. Sometimes we combine them into 1. Least common denominator, very common thing. And then that one that we did where we multiplied top and bottom by a factor that appears on the other side of the identity. So that was like with, which one was that? Like this one. So we multiplied top and bottom by 1 minus cosine, which is on the other side of the identity. We're not clearing it or dividing both sides by, because we can't do that, because we're trying to show the equals is true, and that would be assuming the equals is true. But because that showed up over there, and just because of the Pythagorean identity that it creates, that's a very common thing to do. So anyway, very good idea just to pause and just write these down to get yourself a good idea of some places to go if you're getting stuck.